Good morning. I am Mariam and today our topic is PN junction. So today we are dealing with chapter 14, Semiconductor Electronics, and our topic for today is PN junction. So first let's see what is a PN junction. When a p-type semiconductor crystal joins with an n-type semiconductor crystal, the resulting arrangement is called as PN junction. Wait. What is a semiconductor? So that is first what we are going to be dealing with. Semiconductors. So we know that a conductor is a substance having the highest conductivity and an insulator is a substance having the least conductivity. And a semiconductor is a substance that has its conductivity somewhere in between that of a conductor and an insulator. Now there are two types of semiconductors that we will be dealing with. One is called intrinsic semiconductor and the next is called extrinsic semiconductor. So what is an intrinsic semiconductor? You can say an intrinsic semiconductor is like a pure semiconductor. For example, we know some basic examples of semiconductors: silicon, germanium, gallium arsenide. So let's take first silicon, and I'm taking a couple of silicon atoms here. Okay, who can tell me the atomic number of silicon? Anyone? 14. Atomic number of silicon is 14. So we have the electronic configuration as 2, 8, 4, which means that valence electrons are 4. So let me draw the valence electrons, 1, 2, 3 and 4. Similarly, for all silicon atoms, I will be drawing the valence electrons. There are 4 valence electrons. For now, I will just take into consideration these 4 atoms, the rest we will see later. So silicon has 4 valence electrons, but is it stable? No, it is not stable. To achieve octet, 4 more electrons have to be either lost or gained into the valence electrons, correct? So what we will do is, we will form covalent bonds. What is covalent bonds? Who can tell me what is a covalent bond? Sharing of electrons. Bonds are formed by sharing of electrons. So let's say this silicon atom forms a bond by sharing this electron, this one forms a bond by sharing this electron, this one forms a bond by sharing this one, and this electron forms a bond. Is this silicon atom stable? Yes, it is stable. 1, 2, 3, 4, 5, 6, 7, 8, 8 atoms, 8 electrons are there in the valence shell. So this shows that silicon forms covalent bonds with one another. This is an example of an intrinsic semiconductor where there is no impurity. It's a pure semiconductor. Done? Now we are dealing with extrinsic semiconductor. So let's say I'm changing silicon into phosphorus. So we have all silicon atoms and 1 phosphorus atoms. What did I do right now? I just did a process called doping. What is doping? Doping is the process of adding an impure atom to a set of pure atoms to achieve desired results. So this is a set of pure atoms to which I added an impurity, phosphorus, in order to achieve an extrinsic semiconductor. Alright, so now let us leave these bonds. Okay, let's take into consideration this one bond. I am applying an external energy, say for example 3 electron volts. If I am applying an external energy, one of these electrons which are bonded will have a tendency to jump out. Alright, pay very clear attention because this is a new concept. When this electron has a tendency to jump out and it comes outside, what is formed over here? A vacant space is formed over here. So a negative charge, that is an electron, has just been pulled from this area. So what is the possible charge of this area? Positive charge. This is called hole concept. When an electron is removed from a semiconductor atom, there will be a vacant space and a virtual positive charge is created in this space, and that positive charge is called a hole. Done? So we have basically explained intrinsic and extrinsic semiconductors. Now we will be dealing in detail with extrinsic semiconductors. Now there are two types of extrinsic semiconductors. One is called N-type and one is called P-type semiconductors. So I will explain what an N-type and P-type semiconductor is with the help of a p-n junction diode. So first I will draw the p-n junction diode. Okay, so you can say this is a very rough diagram of the p-n junction diode. Let us consider this as p-type and let us consider this as n-type. So what does a p-type and an n-type semiconductor do? A p-type semiconductor basically has excessive holes. What are holes? We said those are virtual positive charge carriers. So these have excessive holes. So what is the possible charge of this? P-type semiconductors are positive in charge. Why? Due to excessive holes. And we know that N-type semiconductors have excessive electrons. So what is the possible charge of N-type semiconductors? Negative charge. So N-type semiconductors are negative in charge and P-type semiconductors are positive in charge. Now what we are going to do is a very important phenomena, because now we are going to deal with formation of p-n junction. Yes. When an aluminum, now we need to know what are trivalent and pentavalent impurities. What are pentavalent impurities? Impurities having valence shell 5 electrons. And trivalent impurities, valency 3. So now we are dealing with pentavalent. Always keep in mind p-type pentavalent. Sorry, p-type trivalent and n-type pentavalent. So in order to make a p-type, n-type, a p-n junction diode, we do doping here. That is, we introduce trivalent compounds to p-type semiconductors. When this happens, diffusion occurs, drift occurs, barrier potential occurs, depletion layer occurs. These are 4 terminologies that we need to know in order to understand formation of p-n junction diode. So a semiconductor having p-type impurity at one end, p-type impurity, and n-type impurity at the other end is called a p-n junction diode. A diode is a semiconductor, and the junction at which p-type and n-type semiconductors are formed is called a p-n junction. So now let's learn the 4 terminologies as I stated before. Terminology number 1 is diffusion. The movement of majority charge carriers from the majority zone to the minority zone due to the potential gradient is called diffusion. Let me show you with the help of this. Let us consider that this is the p-type semiconductor, and let us consider this is the n-type semiconductor. So what is the charge over here? Positive. And what is the charge over here? Negative. So what happens is, here there is excess of holes. So excess of holes travel from here to here, correct? Majority charge carriers move from majority zone to minority zone. Here holes are majority and here holes are minority. So major holes travel from here to here, from majority to minority. And majority electrons, here the charge is negative. Majority electrons transfer from here to here, because here electrons are in majority and here electrons are in minority. So when electrons transfer from here to here, what happens here? Loss of electrons. So what is the charge? positive charge. Here it was negative, but loss of electrons happens, so negative becomes positive in charge. That is what we see over here. And here loss of holes. Holes are virtual positive charge carriers, and when positive is gone, what comes over there? Negative charge. So there is an excess negative charge in p-type and excess positive charge in n-type. So the movement of majority charge carriers from their majority zone to the minority zone across a potential gradient is called diffusion. Second terminology is drift. The movement of minority charge carriers across an electric field is called drift. Let me repeat once again with the help of the diagram. Here we have excess of holes. Holes move from here to, this is the p-type, okay? Holes move from here to here. So what is in minority? Electrons are in minority. Majority holes, electrons are in minority. So when there is a movement of electrons from here to here, from n-type to p-type, and movement of holes from here to here, what is created? An electric field is created due to the movement of charge carriers. This electric field will be in which direction? From positive to negative by default. So when it moves from positive to negative, are you all following me? I hope you're all following me, you're all blinking. Okay, when it moves from, electric field will move from positive to negative. So it will be from n-type to p-type. The movement of minority charge carriers against the electric field is called drift. So who can tell me which direction will be hole diffusion? Hole diffusion from P to N or N to P? From P to N. Who can tell me in which direction will be electron drift? N to P. So I hope diffusion and drift is clear with all, because now we are dealing with another terminology called barrier potential. The potential difference across the junction caused due to the loss of electrons from N region and gain of electrons from P region is called barrier potential. So what happens here? Here holes are leaving. Here electrons are leaving. So what is being caused? A potential gradient is being caused. This potential gradient reaches a particular point in the middle of the electric field to stop the flow of charges, to stop the flow of charge carriers. This stopping potential is termed as barrier potential. And there's one more term after barrier potential called depletion layer. What is a depletion layer? The layer which is formed near the junction and is devoid of free charge carriers is called depletion layer or depletion region. Let me show you. So here, loss of holes, negative charge, excessive negative charge. Here loss of electrons, excessive positive charge. So at this particular junction, you can see that there is excessive negative charge in the region of p-type and excessive positive charge in the region of n-type. So this particular layer is termed as depletion layer, where the neutral charge is 0. That's all my topic is for today. Any questions?
Yes. So you talked about this, then how can we apply it? Where can it be applied?
Applications of PN junction diode. You can use it in solar cells. There's one more phenomenon termed as forward biasing and reverse biasing. Applying forward biasing and reverse biasing, you can use it in various equipments like resistors, in solar cells, in LED lights. You can use PN junction diodes.
How exactly does holes move? You have said that holes are empty spaces, right?
Yes.
So how does it exactly move from P to N?
I said that holes are empty spaces. I also said that they are virtual positive charges, correct?
Yeah.
Charges move in the presence of electric field, true?
Yeah.
So when there is an electric field, do you want me to show the diagram?
Just explain.
Okay, in the presence of an electric field, when negative charges move from here to here, the positive charges, that is the holes, move from here to here. You understand? when negative charges, that is electrons, what are holes? They are charge carriers. They are virtual charge carriers. They are empty spaces, but they are termed as virtual positive charges. So when negative charges move, along with that positive charges also move. Why? Due to the influence of electric field.
Okay, very last question.
So in a PN junction, there exists a potential barrier and there are minority carriers and there are majority carriers. So how are majority carriers able to overcome the potential barrier?
So your question is, how are majority carriers able to overcome the potential barrier? No, see, the potential gradient is caused such that the flow of carriers stop. When the flow of carriers stop, it is due to the presence of electric field and potential barrier. When there is an electric field, we know there is a potential barrier caused here, correct? So when the potential barrier is caused, the flow of electrons from n-type to p-type and the flow of holes from p-type to n-type stops. There is no flow. So there is no point in the majority carriers overcoming the potential because there is no flow of electrons and holes there.
So how do minority carriers overcome this potential barrier?
Minority carriers don't overcome the barrier potential. They flow in the presence of electric field. It's due to the electric field that these minority carriers are moving. It's called drift. When negative comes here, what automatically goes there? Positive goes there. So there's no role of potential in this particular transition. I hope I've answered your question.
Do you want to?
I see you did not mention about the current. Like, if the electrons are moving from N to P, there won't be a current.
So we know a very general statement, current always opposes the flow of electrons. So if electrons flow from n-type to p-type, automatically current will flow in which direction? From p-type to n-type. That is called drift current. I hope I've answered your question. A diffusion current.
As you mentioned earlier about extrinsic and
Yes.
intrinsic semiconductors.
Yes.
So would there be a difference if they were connected to an external circuit in both the